Hello, everybody. Welcome back to MIT Category Seminar. Today we have David Spivak, who's going to talk about his work on polynomial functor, and in this case, about polynomial comonads and why they are categories. Before I give the word to the speaker, I'm going to tell you about questions. So please, if you have a question, either raise your hand using the Zoom feature or write in the chat, or if you're not on Zoom, use either the YouTube chat or the Zulip channel, okay? So hi, David, and please go ahead.
Great, thank you, Paolo. So today I'm just talking about the fact that polynomial comonads are the same as categories. And this is a fact proven by Ahman and Uustalu in 2016. And their result is a bit more detailed than this, but this is what I'm mainly going to prove today. I've also seen in a previous talk, I gave Richard Garner's proof of this fact in a very abstract way. And today I'm going to do it in a very concrete way. So the plan of the talk is that I'll recall what polynomial functors are, so you don't have to know right now, and the composition monoidal structure. I love how it tells me that I've misspelled all these words. Anyway, I'll introduce this new notation called polyboxes. It's just a simple way of thinking about polynomial functors and the maps between them. And that's going to be the way that we prove concretely why polynomial comonads are categories. And then I'll state some theorems, one of which is this Ahman and Uustalu theorem. And then I'll explain concretely this fact. And possibly I'll get to this other result, which is a corollary of a result by Richard Garner. Basically, so if you have a category C, and again, you can always consider categories as polynomial comonads. Sorry, it's a bit slow. My internet connection is not great. So if you have a polynomial comonad or a category, they're the same thing. The following are equivalent. So you could see C as a category and look at the functors from C to set. And that's a familiar thing. It's a wonderful topos and stuff. Those are the same as discrete op fibrations over C. If you've heard of the category of elements construction, that is many people know this fact. But what you probably don't know if you're not familiar with polynomial comonads is that if you look at the left C modules and you look at those polynomials that are linear. So a linear polynomial is like 5y or 16y. Y is my variable. So if you have a linear polynomial and it's a left C module, that also is a copresheaf on C. And a constant left C module, a constant polynomial is one of the form like 43. So if you have a constant left C module like 43, 43 as a C module structure, that'll turn out to be a copresheaf on C with exactly 43 elements. Representable polynomial functor is one of the form y to the a. If y to the 43 has a right C module structure, then there is a C set, a functor from C to set with 43 elements. It's also C0 bimodules and C coalgebras. So if I have time, I'll get to this too. So let's begin. Polynomial functors. So a polynomial functor is a sum of representables from set to set. So for example, or sorry, not for example, let me say what I mean. So let's say S is a set. So S is in set. Then Hom S blank is a functor from set to set. And it sends x to the s, x to the s power. So I'm going to denote this thing y to the s. Y stands for Yoneda. It also looks like a variable. And so y to the s of x is x to the s. And of course, some of the most important ones are y to the 1, which I'll just denote y. And that's the identity functor, and y to the 0 is 1. Okay. So an example of a polynomial is something like y squared plus 3y plus 2, or natural numbers y to the reals plus 7. Okay. Natural numbers y to the reals plus 7. Again, what I'm saying here is that the sum could be infinite and the representing sets can be infinite. Okay, so as Paolo said, feel free to ask questions in the chat and he'll ask me. So if I want to draw a polynomial functor like y squared plus 2y plus 1, I can draw it in terms of what are called corollas. So these are like a dot with some arrows coming out of that, or that's how I'm going to draw it. So there's y squared, there's y, and there's 1. So the number of, sorry, I'm nervous, I guess. My hand waves when I'm nervous for some reason. There's y squared plus 2y plus 1. And what you're seeing here, yeah, you just draw this, each representable in this way. And it'll come in handy for us to write it this way. One thing I want to emphasize is p of 1. If this is p, then p of 1 is 1 squared plus 2 times 1 plus 1, which is 4. And those are the 4 corollas being drawn here. So I call p of 1 the set of directions. The set of positions of the polynomial. This polynomial has 4 positions. And then if you take one of the positions, and these things I call directions. So the first position has 2 directions. The second position has 1 direction. The last position has no directions. So p of 1 tells you the set of positions. Okay. So I'm going to talk about polynomials in standard form. This is what I mean by that is I just have a certain notation I like for polynomials, polynomial functors. I say that they're the sum over all the positions of representables. And what's the name of my representable? It's p bracket I. If I did p parenthesis I, you would think I was applying p to I. But no, this is just, these are just the set of directions in each position. And if I wrote p sub I, then I wouldn't have any room to talk about multiple polynomials. So that's why I do this p bracket I. Directions in position I. There's another standard form. It's basically the same. This sum symbol is a coproduct in the category of polynomials, so it's fair. This product symbol I'm drawing now is a product in the category of polynomials. So it says that the polynomial is the sum over all its positions of the product of over all its directions of the identity y. So this is what I call standard form. So now let's talk about composition of polynomials. And here I have 2 polynomials, p and q. And if I want to compose them, p composed q, I just take p, and in for y, I plug q. So it's the sum over all positions in p, of the product over all directions there, of the sum over all positions in q, of the product over all directions there, of y. Now let me give you, this is a monoidal product, but I prefer to write this monoidal product with a triangle instead of a circle. And the reason is because I want to use circles later to talk about composing morphisms of polynomial functors. And circle is just too useful to have as the name of my monoidal structure. So I call it triangle. And it's not symmetric, and the triangle symbol is not symmetric, so that's nice. The monoidal unit is y. So this is, so poly with this symbol, and y is a monoidal category. And so let me just give you a quick example. So suppose p is y squared plus y, and q is y cubed plus 1. Then I would draw this one as 2 arrows and 1 arrow, and this one as a position with 3 directions and a position with 0 directions. And now I want to compose them. And so I would write p. It's kind of like a tree growing up. That's how I pick the symbol. P composed q is, I happen to know the answer. So what you do is you, I'm just going to draw it for you. Basically, it's all the ways of putting q on top of p. So for example, you could go like this. You could go like this. You could go like this. You could go like this, or this, or this. So those are all the ways of putting Q things on top of P things. And now what is this? I said a polynomial you're supposed to draw as corollas, but I drew it as two-step trees. So what's really happening is here, what I do is I condense these. So this would be a y to the sixth. This would be a y cubed because it has 3 directions coming off it. I guess technically I should draw little arrows on all these guys. So it has 3 directions off it. This one has 3. This one here has no directions coming off it, so it's y to the 0. This one's y cubed, and this one's y to the 0. And so it's telling me that if I compose P and Q, I'm supposed to get that. Well, P composed Q is basically y cubed plus 1 squared plus y cubed plus 1. And that indeed is y to the 6th plus 2y cubed plus 1 plus y to the cube plus 1. Y to 3 plus 1. And so there's the picture. So again, this little triangle symbol means draw Q trees on top of P trees, but it also just means compose. Okay. Morphisms of polynomials. I'm just telling you what a morphism is here, and then soon we'll get to the real stuff, which is polyboxes, or the stuff that's going to help us in our theorem. A morphism of polynomials, is just a natural transformation. So what is it? Well, it's very easy to calculate because P is just a sum of representables. So I can take that sum out and say it's the product over all positions of polymaps from a representable to Q. And so here I'm just using coproducts. And all the equal signs I draw today, I think, will be isomorphisms. Okay, here I'm going to use Yoneda to say it's the product over I in P of 1 of Q of Pi. So that's the sum over J in Q of 1 of basically set maps from Q of J to P of I. And that's the formula. But I'm going to rewrite it one last time in a kind of set builder notation. It's a set of pairs F1, F sharp, where F1 is a map on positions. It takes every position of P and gives you a position of Q. And then F sharp is a dependent function. So for all I in P of 1, I have an F sharp I, and it's a function from Q bracket J, F1 of I to P of I. And that's another way of writing the set of polynomial maps. You give a map on positions from P to Q, and then you give a map back from Q's directions back to P's directions. It's very combinatorial, but it's still a little hard to remember, and the polybox thing helps you remember it. So what I'm going to do is I'm going to draw a polynomial with two boxes, one on top of the other, and the bottom box is P of 1, it's all the positions. And once you've drawn a position in the bottom, then you're allowed to draw something in the top, and you're allowed to write a direction there. So first you fill the bottom with something, then you fill the top. And I've been starting this institute called Topos Institute, and I've been dealing with a lot of spreadsheets recently. And one thing I learned about spreadsheets is that they have blue cells and white cells when you have a real good admin person. And the blue cells are things that the user fills in with any value they want. And a white cell is a cell that's calculated by the spreadsheet. So the spreadsheet designer makes formulas in all the white cells and tells you it's your job to fill in blue cells. So what I want to use that for is that if I want to map from P to Q, if P is a polynomial and Q is a polynomial, then what I'm going to do is I'm going to ask you to give me a map on the bottom called F1 and a map on the top called F sharp in the notation we had before. And I'm going to tell you that as the spreadsheet designer, I fill in how F1 and F sharp work, and I ask you as the spreadsheet user to fill in anything you want on those blue cells. So the user would come in and say, I want to understand your function, your map F of polynomials. What do I do? Well, I said, here's what you do. You fill in a position, and then I'll tell you what it is. I'll tell you what F1 does to it. And then you fill in a direction there, D, in Q of F1. See, we're looking back here. Someone fills in a direction D there. And then we tell them F sharp. We're allowed to use I as data of D. So that's how polybox morphisms work. But the way where they really shine is in maps to a composite. So a map, when we're talking about comonads, because today we're going to be talking about polynomial comonads. And these are all about maps from P to a composite of P's. P to the empty composite and P to the twofold composite. And then associativity is like whether maps to the threefold composite are the same and stuff. And so luckily polyboxes work really nicely in maps from a polynomial to a composite of polynomials. And the formula we had for morphisms of polynomials say that we're supposed to take the product over the positions in P, and then we're supposed to kind of put in all the Q stuff. And when we look back at the definition of the composite, it's just a sum of products. So there's the formula for the composite of P and Q. And so now we're ready to say what a morphism from P to Q1 through QK is. It's for every position in P, a choice of position in Q, and for every direction in Q1, a choice of position in Q2, and for every direction in Q2, on and on and on until you get for every direction in QK, a position back in I. So it's like a lot of stuff going on there, right? It's kind of hard to remember all that. But the polybox thing makes this very easy. So here's P, and here's how Q looks. Q1, and then stack on top of that Q2, and then go all the way up until you get to QK. And you tell me what F1 is. You give me a bunch of the spreadsheet designer gives me all these functions, F1, F2, F3, all the way up to Fk. And then they give me a map down called F sharp. And this whole thing is F. That's the morphism. Except it's useful to tell the person where they're going to need to fill data. So the user is allowed to put anything they want here, 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 here. And the spreadsheet designer, the person who made F, has to fill in the white cells once they do. So if you want to give me a function, if the spreadsheet designer gives F, it is a way of dealing with any way a user can fill in the blue cells and filling in the white cells accordingly. All the little Fi's and F sharp are functions. They just happen to depend on stuff already filled in. They're dependent functions. So let's say you have a map between linear polynomials. Let's say P is AY for a set A, and Q is BY for a set B. Maybe you already know what the polynomial maps from AY to BY, what all the natural transformations from the functor that takes a set and multiplies it by A to the functor that takes a set and multiplies it by B. But here's how it would look in polybox notation. One last piece of notation is that when there's a unique choice, I fill it in with gray. So a polynomial is linear means that once you choose the position, there's only exactly one direction there. So I fill that in to say that it's unique. It exists, but there's only one of them. But there is data in this part. So if the user fills in an element of A, all I have to do as a spreadsheet designer is give an element of B. So it's exactly just the set of maps from A to B. Whereas, another thing you could do is you could say, suppose P is y to the A, a representable, and Q is y to the B. Then you may know that the set of maps from y to the A to y to the B is the set of maps from B to A. And how does polyboxes show that? Well, a representable is a polynomial where there's only one position. So there's no data down here. There's data here, but right. So it looks like this. Okay, so to give this map, I need to give F1 and F sharp, but F1 is unique because it's a map to a singleton. And so all of the data is the user fills in an element of B, and it's our job to give them an element of A. So we do get back this thing. Okay, I'm going to tell you, wait, is it? Let's see. Yeah. Okay, I'm going to skip ahead a little bit. So this is how polynomial functors are represented by polyboxes and how morphisms to composites work. Let me give you the theorems that we're going to try to prove today. Well, sorry, we are going to prove this first one for sure. Up to isomorphism, comonoids and poly are categories. The morphisms of comonoids are not functors. They're something that people are calling cofunctors. I'm not a big fan of the name, but I'll get to that in a little bit. Garner, in a theorem he described in a video, showed that for categories C and D, which you can consider as comonoids and poly, the category of CD bimodules is equivalent to the category of parametric right adjoints from D set to C set. Now, parametric right adjoints are what I call in databases data migration functors. They're also unions of conjunctive queries, if you like those words. They're also connected limit preserving functors. But they're very general thing. They're pretty general things. And they're useful in higher category theory. Jamie Vickery told me recently that when C is the globular indexing category, his way of thinking about infinity categories is as a certain sort of parametric right adjoint from C set to itself, so from globular sets to itself. But anyway, I'm not going to be able to prove Garner's thing today, not because, so the polybox stuff does work for this. It's just a little bit long as a proof. But what I am going to try to prove today is this corollary. It's not quite a corollary, but if you understand Garner's theorem, then this one will be easy. So if you have a category C, and again, categories are polynomial comonads, then you can talk about its comodules. Oh, I talked about this before, right? So these guys are in terms of C as a category, C as category. And these guys are in terms of C as comonoid. Sorry for that. Okay. So we may get to this today. Okay. So why are categories? So I think we're like at the parking lot of Disneyland now. If the goal, if the ride we're really looking forward to is this proof that comonoids are categories, we're getting fairly close. I'm ready to define what a comonoid is now. So a comonoid in any category, in any monoidal category, but in particular with poly and this monoidal structure, it's a tuple C. C is going to be a polynomial. Epsilon is a map from C to the identity functor. And delta is a natural transformation from C to C composed C. And it satisfies these conditions that if you do delta and then epsilon, you get back to the identity. And if you do delta twice, it doesn't matter what order. Now, in terms of polyboxes, these are the pictures I'll be drawing. So I have a map from C to Y here. This is Y. Y is both linear and representable. And so it only has one position and one direction. And so to give a map to Y, I don't really give, for every element of E here, I give an element of the unique of the singleton set. And for every element of the singleton set, I give an element, a direction. And so a map from C to Y is just a map for every position, you pick a direction. So D is in C bracket I. It's a direction for every position. And that's going to turn out to be the identity, the identities. But we'll get to that in a second. Delta, right? Delta is this thing. Okay. Cool. All right, so let me give you now the idea. Why are categories comonoids? How is this going to at all work? So here's a definition. Let C be a category. And for every, just some notation, for every object, oh, by the way, when I say category today, I mean small category. For every object I in C, let's say ob C, let C sub I be the set of F from I to I prime in ob C. So C sub I is the emanating set of emanating maps, the maps out of I. So here's the definition. The emanation polynomial of C is sum over all objects of y to the ci. And I'm going to call that little c. So this polynomial, yeah, I find it to be very nice notation also. If you have a polynomial, if you have a category and you want to denote it by something, you could call it c or d or e, but you could also call it y to the 5 plus 2y squared or something. So this is the emanation polynomial. It just organizes your category in terms of objects and maps out. And the idea is that the co-unit from C to Y is going to tell us identities. It's going to give us for every position, in other words, object. So the objects are the positions, and these are the directions. The outgoing maps are the directions. So the epsilon is going to tell us for every position and outgoing map, and it's going to be the identity. And delta from C to C composed C is much harder to see through what that does, but it's going to give us codomains, because we don't know what those are yet, and it's going to give us composition. And that's our goal, is to use polyboxes to show how that works, and that the axioms for a category, the axioms for a comonoid force this to work. So it's going to help us if we choose appropriate names for things. So here's C, and here's epsilon. Sometimes I like to write it in red for some reason. And here is epsilon sharp, but instead of calling it epsilon sharp, I'm going to call it ID, identity. It's a map from every position to a direction there. And it's also going to help to have a name for the maps for delta. This one is going to be called delta 1. And soon we're going to learn that delta 1 is forced to be the identity. This one's going to be called cod, but it's just a name right now. And that one's going to be called composition. So my goal is to show that the thing called cod really acts like codomains, and the thing called comp really acts like compositions. And that delta 1 is always identity. Okay, so great. Let me give you some examples of emanation polynomials. So consider the walking parallel arrows category. What is its emanation polynomial? You can try to think about that for a second. So it's a sum over all objects of the set of maps out. I'm also going to look at the poset n less than and tell you the emanation polynomial for that. You can try to figure out what that is while I'm talking. What is the emanation polynomial for that? And also its opposite, n greater than, which looks very different. It's a totally different category. It's got a terminal object where the other one had an initial. Its emanation polynomial is quite different. So what is the emanation polynomial of C, of the walking parallel arrows? Well, the first object has 3 maps out, and the second object has 1 map out. And that's a pretty disambiguating name for a category, y cubed plus y. There are at least, I think there are several, maybe 3 or 4 different categories with that emanation polynomial. But there are many categories whose name is C. So it's disambiguating in a certain way. This one, the emanation polynomial of this guy, well, there are natural number many objects, and each one has natural number many things coming out. It's got a length 0 string, a length 1 string, a length 2 string. So it's sum over I. It's n y to the n. Whereas this one, the first one has only one coming out, one outgoing morphism. The second one has two, so it's this. It's y plus y squared plus y cubed plus dot dot dot. Very different emanation polynomial. Yeah, so let's look at the poset of naturals here. If I wanted to tell you what is the map IDY here in n less than, well, it's just saying that if you pick one of these i's, what is the name of the outgoing morphism that is the identity? The name is that it's the natural number with, it was 0 arrows, so that's the identity. It sends I to a map coming out of it, namely the map of length 0. And so that's epsilon. And for delta, we would have, turns out that the comonoid structure here for delta, once we get to the proof, and we could backtrace this and see, but for right now, I just want to tell you how it works. Okay, so if someone comes in and they say, you have n and n and n. Each one of these is ny to the n. And so someone comes in and they say, tell me about I. So they pick one of these objects. How does delta work? Well, I told you that later we'll see that delta 1, the bottom thing, is always going to be forced to be the identity. So I'm allowed to define delta any way I want right now because I'm not constrained. But I'm telling you what delta will eventually be. Now someone gives us a number of, like a length of path out, say m. So they say, I want to go 5. And we're supposed to give them cod here. So we say I plus m. And then they give us another number of arrows out, n. And we're supposed to give them composite here. So we give them m plus n. I don't know if this is helpful or not, but this is how it's going to work. So we're going to compose this map cod here, gives us the codomain of this outgoing morphism. And this map semicolon here is going to give us the composite of the two blue things, m and n. So let me give you one more example. If you have a monoid as a polynomial, its emanation polynomial has a special feature that it's completely, that is representable. So it's of the form y to the m. The map identity, IDY, is going to take our unique thing and return E, the unit of the monoid. And the delta, which is supposed to give us codomains and composites, is going to work like this. Let's see. These are all representable. We're supposed to fill in something here, here. So on the, sorry, I might not have made this explicit. On the domain side, we fill in the bottom, and on the codomain side, we fill in the tops. That's just how it works. Okay, so, someone gives us a unique piece of data in that thing. We give them back the unique thing here. They give us an element of M, an outgoing morphism. We take its codomain. They give us another outgoing morphism. We compose them. Okay. So that's how delta and epsilon work in the monoid case. And now we're actually ready to prove the results. So this is, we're getting on the ride for the Disneyland thing. So this is it. Okay. So the first axiom for comonoids is written in red there. It says that if we do delta and then we do identity composed epsilon, it's the same as doing identity on C. So on the left here, I've drawn delta and then identity on C and epsilon. And on the right, I've drawn identity on C. And we're supposed to show these two are the same thing. And to do that, we fill in an object of C. We fill it in a, whoa, my iPad just does that sometimes, sorry. We fill in an object of C. We fill it in over here also. And we start going. So the spreadsheet designer says delta 1, apply delta 1, we get delta 1 of I. We don't yet know that delta 1 is identity. We will soon. And then the spreadsheet designer says copy it over. He or she says, give me an outgoing morphism. So we're like, okay, F comes out of I. And it says, fine, I fill that in with identity. And it says, the spreadsheet designer says, okay, take codomain of F. Okay, done. Take the identity on that. Okay, let's call that identity sub cod F. And then they say, okay, now compose. And what we're supposed to compose is F with the identity on cod F. So we go F composed identity on cod F. And we're done with that side. Let's do the other side, fill it in the same way, and do the identity map of polynomials. And we're ready to extract what this axiom is telling us. This axiom is telling us that this is equal to this, and that this is equal to this. And so what we're getting is that delta 1 of I is I. And that's the thing I told you before. We're now allowed to replace delta 1 everywhere with just identity as a function. And it's telling us that F composed identity on the codomain of F is F. That was smart of it. Good job, polynomials. So we have these two axioms now. And they follow from, the first one is just bookkeeping. Delta 1 of I being I is just something for us. But the second one is one you would recognize. Okay, so let's do it again. So we're supposed to fill in an object of our category C. And then we're supposed to use delta 1, but we know that thing's identity now. So it's just, we return the same object, I. And then we look at identity on I. Cod of identity on I. Cod of identity on I. And now the user fills in a morphism that comes out of cod of identity on I. They fill in any outgoing morphism, we copy it and compose. And we just fill in the other side, I, F, F. And we learn two new things here. We learn that this is this, and we learn that this is this. So we learn that cod of identity I is I. Is that good? Oh, that's good. Yeah, I thought I already did that one. I got confused. Cod of identity on I is I. That's good. Good. Thank you. Thank you, polynomials. And they also tell us that identity on I, if you compose with F, you get F. And that's also very smart of it to know that. I don't know how it knows these things. I just find it amazing that it knows these things. But anyway, so last thing it knows is that delta, a comonoid has this last property. Let's fill it in. So, oh, let me show you the property. So you see that pretty picture there. Okay, yeah, so let's fill it in. So we pick an object in C, and we copy it over, and we copy it over. We fill in an outgoing morphism, we copy it over, we take its codomain, copy it over. We pick an outgoing morphism, we take its codomain, we take an outgoing morphism, we compose, and we compose again. And we filled in the left-hand side. And now we're going to see what the right-hand side does and then see what the equation is telling us. So we fill it in the same way. We have I, F, G, H. But let's fill in some stuff. So this is cod F This is then F composed G. This is cod of F composed G. This is copied over cod of F composed G. This thing is just H, and now this thing is F composed G composed H. So let's see what we got. We know that this is this, this is this, this is this, and this is this. Okay, so what do we get? Well, we got that I equals I, that's no data, not important. Cod F equals cod F, okay, we already knew that. But we do get a new thing. We get that the codomain of G is equal to the codomain of F composed G. That is true. And finally we get, or that is true of categories. And finally we get that F composed G composed H equals F composed G composed H. And that was supposed to be, and I hope it was, the simple demonstration that codomains, that comonoids are categories. Okay, I mean, I think maybe I could stop and ask if there are questions. The next thing we're going to do is talk about cofunctors, and then maybe get to this last thing about linear left C modules and stuff. But if there's any questions.
Okay, any questions? So far, there is a comment by Todd. I don't know if Todd, you want to elaborate on that, or was it just a thing from before?
Oh, the alternation of sums and products reminds you of games. Yeah, me too, for sure. Yeah, yeah, I think that's really a fun thing. Do you have anything to add?
Not to that. It was kind of a throwaway thought, but oh, can you hear me, by the way?
Yes.
Yeah, also what you're describing here is very reminiscent of the fact that in topos theory, you can regard an internal category of a topos as inducing a lex comonad. This is very, very similar.
Interesting. Yeah, I'd be happy to talk more about that at some point. Okay, so let me talk about maps between comonoids. And people are calling these cofunctors, but I don't really like the name cofunctor. I don't know whether we're early enough in this world, in this field or whatever, to rename them, but they were named by Marcelo Aguiar. And the problem with that name for me is that they don't feel at all like functors. So here I'm saying, we think of a functor F from C to D as like giving a picture of C inside of D. You might think of it that way. A cofunctor, you can think of giving a D-shaped sorting of C. So I'm proposing, and I don't know if it's a great name, but I'm proposing sortor. Like function is to functor as sorting, sorting is to sortor. But I don't know what to call these. I just don't like cofunctors because they're not co. They're kind of backwardsy and they're kind of forwardsy. But anyway, here's an example of a picture. If you have a category D, the emanation polynomial for this would be y to the fifth plus 4y. It's got one object that maps to four others. Then a cofunctor to it, or a sorter or whatever, basically draws that picture throughout C. It says that every object in C is sorted into one of those 5 sorts, and every morphism, and every object that's given the central sort has to be given 4 maps out to those other 4 sorts. So it kind of like crystallizes your category, or like makes everyone have a phone tree to their neighbors or whatever. So every object in it doesn't say that C only consists of these morphisms, but it picks out within C. It sorts the objects of C into these 5 sorts and then picks out these 4 different morphisms for every object, every central object. So you can see it. I mean, it's kind of, yeah. I don't know. So so another way to think about it is that a cofunctor is a map between comonoids, and so it has a certain map on the underlying polynomial functors. So it's gotten a certain natural transformation involved. And if that natural transformation is Cartesian, then a cofunctor would be a discrete op vibration. A Cartesian cofunctor is a discrete op vibration. And a discrete op vibration you can think of as sorting your category of elements into your category, into your base category. It's a database instance, if you like that terminology. So cofunctors, those are the, yeah, cofunctors are kind of like sorting, ways of sorting. Okay, so let's say you have two categories. A cofunctor between them is a morphism of them as comonoids. Remember, categories are polynomial comonads. So it's a map of the emanation polynomials C to D that respects codomains and compositions. So to draw it with polyboxes, it's this map from the emanation polynomial of C to the emanation polynomial of D, called phi, say, such that when you do phi and then identity, it's identity. And when you do codomains and compositions, delta, and then phi, it's the same thing as doing phi then delta.
Davis, we have a comment from Jochen Koch who's saying it's up vibration backwards, right?
No, up vibration forwards. A Cartesian cofunctor is an up vibration forwards.
Okay, so
it is the case, a vertical cofunctor, one where the polynomial, map of polynomials is vertical. In other words, identity on objects or is the same thing as an identity on objects functor backwards. So maybe that could be what Joachim's thinking.
I see. It says okay.
Great. Okay. So cofunctors or sorters or whatever we call these things are, if someone asks me what's better, functors or cofunctors, functors are essential throughout mathematics. They're obviously better. They're so much better. But cofunctors are neat things. They are things that exist between categories. The category of monoids op is fully faithfully embedded into functors, into categories and cofunctors. It's a totally new way of like comparing categories. I mean, not totally new. It's been around for a little while, but it's different and people are not used to it, and it's interesting. So I do think it's worth looking at. So consider the monoid n0 plus. The emanation polynomial is y to the n. A cofunctor into it. This monoid as a comonoid in poly is co-free. So a cofunctor from C to y to the n is actually a map of polynomials from the emanation polynomial of C to y. And so basically what it means is for every object, you pick an outgoing morphism. And I could call that a direction field on C. Imagine a category C, and for every object, pick any outgoing morphism. You could pick the identity, but pick anything else. Then it turns out that direction fields on C form a monoid. And that's part of an adjunction. So every monoid gives you a category. Every category gives you a monoid by its direction fields, and those are adjoint. And in particular, since isomorphisms of, cat sharp is what I call categories and cofunctors. Since isomorphisms in cat sharp are the same as isomorphisms in cat, so that's a good fact to know. Direction fields on C is an invariant of a category. For every category, there is a monoid associated with that category, and that is an invariant of the category. So that's kind of you can disambiguate two categories by seeing that their direction fields, monoided direction fields, are different. Okay. So I like the alliteration here. Linear left modules and representable right modules are the same thing as copresheaves. So let's say you have a category C. You can think of it as a comonoid. Then the functors from C to set are, the category of those is equivalent to the category of linear left C modules or representable right C modules. And I just mean that the polynomial underlying the C module is linear or representable. So what is a module? If you have a comonoid C, a left C module is a pair M lambda, where M is a polynomial. Lambda is a map from M to C composed M, satisfying these usual commutative diagrams. And so I'll use this this name, assign, apply, and return. Right. So it goes from M to C composed M, or we could do from M to M composed C. That would be a right C module. Okay, so using polyboxes, suppose M is linear, so it's E times Y, it's 53Y. What is a left C action on it? Well, it's this lambda thing. So so here's what's going to happen. A functor from C to set, maybe I for database instance, you can take its category of elements down to C, and that is basically how this linear left C module is thinking about things. E is going to be ob of this category of elements. And pi is the assign. So given E in E, I have pi of E is an object in C. For any outgoing morphism, well, a discrete op vibration says that you can apply that outgoing morphism to E. Yeah, I hope that makes sense. So I'll just call that E dot F. And then for the unique thing here, I get the unique thing there. So there's no data there. And so it's saying that a discrete op vibration is completely determined by how you take a set of elements, you say how to assign each one of them to an object in C, and then you say how a morphism coming out of that object in C gives you a new element of E. And that's not enough yet because we don't have the axioms, but once we do, we'll be done. That will be a discrete op vibration. So it says if I have E and I assign it to pi of E, some object, and I take the identity on pi of E and I apply it, so that's E dot identity on pi of E, that's supposed to be the same thing as E like that. And so we say that this equals this, and this equals this, but that's no data. So what we're getting is that E is E on identity on pi C, pi E. So it says that when you apply the identity, you get back E, and we also would say, let's see, you have some element E, you assign it, copy it, you pick an outgoing morphism in C, F, you copy it, you apply it. What's that mean? Oh, right, E dot F. We assign it, that's pi of E dot F. We pick an outgoing morphism, we apply it. What's that called? E dot F dot G. And the rest is gray. It's all unique. No data there. And over here, we write EFG in the same places. This is pi of E. This is pi of E. Cod of F. This is happening in the category side. F compose G, apply, that's E dot F compose G, copy it, E dot F compose G, and that's it. And we're supposed to, what we find is that this equals this, this equals this, this equals this, and then no data here, 1, 2. So this is, of course, telling us that where is E dot F assigned? It's assigned to the codomain of F. And what is E dot F when you apply G to it? It's E of F compose G. So my point here is just to show you that this polybox notation makes these sorts of calculations very easy. I think I'll stop here. So thanks.
Thank you, David. Okay, does anybody else have any questions or any comments or would like any clarification? In the meantime, we have a comment from YouTube. It says, I like the bracket notation. Looks like array notation from most programming languages.
Nice. Thanks, Joachim.
By the way, Joachim, if you're able to unmute yourself if you want to say.
No, I just said it's beautiful. But I told him before, but each time it's more beautiful.
Thank you. So just by the way, I'm writing a book with David Chaz Myers, where his part is about these kind of general dynamic system doctrines, and my part is about polynomial functors, which is a particular doctrine. And so if you want preliminary notes, I'm happy to send some of that your way. Or if you'd like a copy of this, well, I don't know if I can make a copy of this thing I made today, but I can try. Just email me.
Yeah, that's nice. Okay, so Brian Pinsky has a question. So Brian, you're able to unmute if you want.
Hey, so I'm used to I'm used to talking about like internal categories. And like the polynomials is still not something I'm super familiar with. I remember there was a remark made earlier about this looks like internal categories in a comonad. Or this looks kind of like that. Is there a way of like, if I work in like some topos and define some kind of internal analog of polynomials, is there a way of seeing how that's connected to
Yeah, internal categories or something. I don't know. I haven't tried. Everything feels constructive, so I don't see why it wouldn't work, but I also I have not tried at all, so I can't say.
Okay.
It's also very element based, so I don't know. I mean, well, I guess, yeah, I don't know.
I mean, it feels like it might be the sort of thing that just kind of you think about for a while until you get a headache, but.
So Christian seems to be asking, can you give more intuition about, maybe if you could unmute yourself, why morphisms of polynomials go forwards on positions and backwards on directions? So intuition is one thing, and then just checking the formula is another thing. So here's the formula, and maybe unmuting and telling me what sort of thing would be useful beyond this.
Yeah, I guess I just wanted to see this argument again.
Yeah, okay, great. So what's happening is that every polynomial is a coproduct of representables, and it's very easy to map out of coproducts, and it's very easy to map out of representables. So when you map out of coproducts, you get a product of all maps. Mm-hmm. And then so the first line here is saying that I can pull the coproduct out. And then the second line there is saying that I can pull, well, what's it saying? It's saying it's Q evaluated on P bracket I. Mm-hmm. Well, Q evaluated on P bracket I is, well, it's this thing with P bracket I in for Y. And, and that's what I wrote.
Yeah.
So it's funny, like when you think about maps between presheaves or copresheaves, we don't think about something going forward and something going backwards. Mm-hmm. But the reason is because, I mean, what makes these special is that they're not just any old colimits of representables, they're coproducts of representables. Mm-hmm. And that, I guess, makes it more compelling to think about it as that forward on those, on the indexing set of the coproduct, and then backwards on the representables.
Yeah, it's really interesting that a Yoneda argument can flip directions around like that. You don't see it happen very often, or you don't see that utilized very often.
Yeah, and for people who are familiar with lenses, there's a thing called lenses. They might write AB mapping to ST or something like that, but I'll just say CD. And they have a forward part called put, and they have a backward part called get. And this is exactly the map of polynomial functors. If you don't know what a lens is, you don't really have to. It's the map from by to the A to dy to the C. To map from B to D, and then B, A, D, C, like that.
Mm-hmm.
I don't know if that's useful, but yeah.
Yeah, yeah.
It just is.
Yeah, thanks.
Sure.
Is it related actually to the fact that, I hope I get this in the correct direction, that co-powers are functorial and powers are functorial in the other direction? Like, for example,
Yeah, that
inverse
sounds
category
nice.
theory?
That sounds nice, yeah.
Okay, so before Sophie, we have a question from YouTube. Does this description extend to operads? And if yes, how?
So operads are close to maps from like a composite of, P composed P to P. They're close to just monads instead of comonads. Oops. The thing is that these maps have to be Cartesian. The problem is that polyboxes don't help you map out of a composite. So I would say this does not really help you with that. Maps out of a composite, you don't get this nice, where was that picture? You see how like this F almost looks like a cobordism or something. It doesn't work the same way going from a composite to a composite, say, or from a composite to a polynomial. So I would say no, at least not as far as I know.
Okay, I hope this answers the question. Otherwise, please keep writing in the comment. Sophie has a question. Sophie, you are able to unmute yourself if you want.
So I see that she's asking, do polyboxes help you think about dynamical systems? Maybe. So I don't really, I mean, they help you in a certain way, but let's see, what can I say? So remember the spreadsheet designer thing? I don't know if this is the kind of answer you want, but in some sense, when you have two dynamical systems that are wired up to form a new one, it's as though each of the two dynamical systems is a little spreadsheet maker, and they're filling in each other's boxes. They're filling in each other's blue stuff with their own white stuff. So yeah. So that's kind of how that works. But did I answer your question? I don't know. I would say I don't.
Like,
yeah.
I know there's a relationship between like poly and dynamical systems. So like, do these like really beautiful way of representing poly help you think about that at all? So.
Yeah, I mean, it helps. It helps me because I don't compose that often. Polyboxes are really most useful when you're going to be composing on one side. But in general, yeah, it does, like just writing out what a morphism of. So a dynamical system is a map from sy to the s to p. And so that means that this thing is s, this thing is s, this thing is p of 1, and this thing is p of whatever. Mm-hmm. And you have these two maps going back and forth. And yeah, it just says for every state, you get a position. And for every direction out of that position, you get a new state.
Does composing the boxes on the right mean anything in dynamical systems world?
It means that S is going to not just give you position in P. So imagine that what I'm doing is I'm delegating. So imagine that a polynomial, these are decisions to be made. So I have 4 possible decisions. One with 3 options, another one with 2 options, another one with 3 options, and one with 1 option. And so a map says that for every decision in P, I'll name a decision in Q. And for every, and a way, given an option that you pick in Q, to turn that into an option in P. So I'm kind of like delegating. P is delegating to Q. Say, whatever position I have 3 options. You flip a coin. If you do heads, I'll do my first option. If you get tails, I'll do my second option. So when you delegate to Q1 composed Q2, you're saying I'm not giving it to Q1. I'm saying for every decision I have, I'm going to give Q1 a decision, and then for every option it can take, I'm going to give a decision to Q2 to make, and then for every option Q2 makes, I'll give a decision for Q3 to make, and then finally, whatever it says, I'll turn that into what option I'm going to pick. So it's like a multi-step delegation procedure.
Thanks.
I don't know why that's useful yet, but it seems neat somehow.
Yeah, seems like hierarchical planning or something.
Yeah, exactly. The launch codes or something. Yeah.
Okay, there's a question from the Zulip channel. Is this category of polynomials the opposite of the small coproduct completion of set?
I would have, the opposite of the small coproduct completion of set. I don't know. One way to think about it.
Sorry, they say small. It's opposite of the small product completion.
That sounds more right. That sounds more right. So the objects, I think so. So an object you can think of as a map from I to set. That's a polynomial. I is the positions, and for every position you get a set of directions. And a map from one polynomial to another is this sort of thing. So you could call it like set slice over set or something. I don't know how people would denote this, but some kind of oplac slicey thing. And I think this may be the free product completion of set, but I don't know.
Yeah, we should probably say free product completion, because somebody was pointing out set, of course, is complete and co-complete. We're talking about adding products freely, of course, like presheafs do with colimits. Okay, there's another remark. The category of polynomials is given by cocart of 1. Yeah. Okay. Probably it's as Christian Williams is saying, it's probably the ordinary coproduct completion. Yeah.
Product? I don't know.
So yeah, it's probably the ordinary coproduct completion, like freely. Sounds about right to me.
Okay.
And somebody's saying there appears to be no nleft page for cofunctors. Could somebody fix that? Yeah, it would be nice to create an nleft page. Actually, it's a pity that Bryce Clark is not here, I guess, because of
maybe it's 2
time zone issues. Like, it's a very bad time for Australia, but yeah, like we should probably.
Yeah.
We should probably.
I mean, I don't know. Maybe I'm the only one who doesn't like the name cofunctor. But yeah. I would prefer another name if it's not too late.
Yeah, I don't even know. I don't know who are the people that use that. Okay, so are there any more questions or comments? If you make the nleft page, you get to name it. Well, yeah, but there's always renaming or multiple naming, so I guess to some extent. Okay, any more questions or comments?
What's
yeah, Todd, please. Okay, you can speak if you want.
Okay. Yeah, I was just asking, you probably said it and I missed it, but how would you describe a functor between categories? in this framework?
I don't know of a way.
Oh,
So there's an equipment, a pro-arrow equipment, where the objects are categories. The morphisms are these cofunctors, and then the horizontal things are bimodules. And this is an equipment, so any cofunctor gives a left and right adjoint. Bimodules by Richard Garner's theorem are parametric right adjoints between D set and C set. So, okay, I'm not answering your question at all. The answer is I have been trying to find functors in here for a while and I can't find them. I don't know. Both functors and cofunctors give you left adjoint PRAs, but I don't know how to characterize all the left adjoint PRAs. I don't know anything about, I don't know anything about functors. I wish I did. I would love to find functors in here, but I can't. I can find reflexive graphs, because I can find copresheaf categories. And then maybe we could put a monad on that, a PRA monad on reflexive graphs, where I would find the categories, the category of categories inside that way. But it's pretty deep. You take polynomial comonads, you take bimodules between them, you look at a certain polynomial comonad, the one indexing reflexive graphs, you look at RA from it to itself, you find it to be a monad, and then you take its algebras. But that's, yeah.
All right, any more questions or comments? Seems no, so we can move the discussion online. And of course, you can still stay here if you want to hang out a little bit. The Zulip discussion is linked in the chat. There's an invite link that you may need if you've never been there. So for now, let's end the streaming. And of course, let's thank David again for a nice talk.
Thank you.